Swayam Prabha. Digital India. Educated India.
You all had good Sunday break. I did. Had a great trip to Mahabalipuram. It's fun.
That's cool. We saw some spectroscopic structures.
Exactly. We didn't do Q-tip on Mahabalipuram. All right, so let's kind of recap what we have done so far. In the first day, on Friday, we started by reviewing time-dependent quantum mechanics, basically to find methods to solve time-dependent Schrodinger equation. In that context, we defined what is called time evolution operator, exponential operator. The time evolution operator. Actually, this isn't the most generalized version of any kind of evolution operator used to kind of propagate my wave function either in space or time. We have briefly discussed how one could expand this out and write out the wave function using such time evolution operators in the context of what we call as a Dyson operator, basically perturbative expansion of the integral. We're not going to use much of that, but what we are going to use is, of course, perturbative expansion of the density matrix. So also going beyond the Schrodinger picture, we have discussed how it is more convenient to work in this representation called interaction picture. I'm going to just write down key words here. Interaction picture. And we are not going to deal with wave functions per se, but we are going to deal with density matrix, which is basically a projection operator. And one could write out the time evolution of the density matrix in the same way. Equation of motion of the density matrix. Everybody remember?
I by H cut, commutative bracket of H computer.
Basically, in the interaction picture, this becomes even simpler because now what we need to worry about is a time-dependent or time-independent interaction potential that the density matrix is transformed into the interaction picture, right? What is this? We remember always, again, this is something that should be tattooed on your brain, is that in the context of spectroscopy, your Hamiltonian will have unperturbed part and an interaction part, which is a time-dependent part. Usually unperturbed part is not, is given to you. The material, you make the material, you get H naught, okay, with its own eigenstates. And then you have a time-dependent part, which is potential. And in the context of light-matter interaction, V-coupling limit, V of t is minus mu dot E. We have kind of derived this from first principles. We have also seen what kind of approximations we have made, so on and so forth. It will also be written in the context, in the form of the vector potential. So this interaction Hamiltonian is related to the dot product of the vector potential and the momentum operator, but could make a dipole approximation and write it again in the field, but mu is a dipole moment operator, which means any kind of transition. You can think of it to have an associated transition dipole. And because it's a quantum mechanical entity, it's an operator. Okay, cool. So we have kind of defined this. We have not used the density matrix, but in the last class, if you remember, we kind of went through resonant driving of a two-level system, and simply in a two-level system, I have two amplitudes to kind of keep track of. PKs interaction picture. So I can write my B0, B1 and track the evolution of it. And we have kind of discussed what are the various consequences. The biggest consequence to kind of take away from that is that when I'm driving the system close to resonance, you could use an approximation called rotating wave approximation. We'll keep coming back to this throughout the course, particularly today. I'm again going to use this extensively. But rotating wave approximation simply means that there are components which are very time varying slowly, some components which are oscillating at extremely fast speeds, much faster than the driving field. And in such scenarios, the response, you're not sensitive to that, so you kind of ignore that. So rotating wave approximation, kind of you move on to a different reference frame in that sense. Okay, and we use rotating wave approximation, but we have also shown that the probability of finding a particle in excited state, that function looks like a Lorentzian function. That's an important thing. So when you drive with light, you're going to generate a coherence in the system. You're going to generate a coherent superposition between your ground and excited states. Kind of makes sense, right? So if when you make your material H0, your ground and excited states are eigenstates of the system, which means if I take a projection of your ground state onto excited state, because they're eigenstates, they're mutually orthogonal to each other, which means the projection should be zero. The light comes, light is a perturbation. Light is a perturbation, so in principle, your previously diagonal Hilbert space is no longer diagonal because now you're adding on the system. But we are making this huge thing that it's a weak perturbation. So we are saying more or less the eigenstates are remain going to be eigenstates, but now I'm going to generate some kind of projection between eigenstates driven by the dipole moment operator. That's a kind of picture. Okay. All right. So these are the few things that we have seen so far. We have also seen another important thing is that I have the Hamiltonian is not really complete here. We have written this. One important part that we are missing here is that your Hamiltonian has H0, which is your system, plus V, which is your light matter interaction, but also what we call a system bath interaction, right? And typically, bath is some kind of broad distribution of energy eigenstates. Okay, and there is some degree of interaction. Now, what is the mechanism of interaction? What is the kind of specific nature of the Hamiltonian? That depends on what is the system, what is the bath, so on and so forth. Like I alluded to you in the previous lecture, the bath could be bunch of crystal phonons. Okay, and then electron phonon scattering becomes the primary system bath interaction parameter. Okay, today I will show you, in fact, this bath could also be all the photon modes available to you, sort of vacuum photon modes. Okay, and then your system bath interaction could simply be spontaneous emission of light. So you take your quantum state, dump the energy into your bath, and this bath happens to be photon bath, and then it will appear to be an emission. And that's also bath, and this is a broad distribution, a continuum of states. Right? So typically your system bath interaction, this part is perceived ground excited state, and these are all your bath states. And you have some kind of coupling between them driving this. And we have seen in the previous lecture that again, in a Schrodinger picture, we're not dealing with density matrices. We are still dealing with we're interaction picture, but not dealing with density matrices. We're dealing with wave functions. We have seen that the probability of transition from the system to the bath is given by Lorentzian. Okay, but now this probability is going to manifest in the response of light matter interaction. Okay, that is spectacular because now coming with light, basically I'm driving this with some field, time varying field, I'm able to read out this term. Okay, that is the strength of spectroscopy, and there is a point of spectroscopy. Point of spectroscopy is I have a quantum system which is evolving, which is not isolated, which is interacting with everything around it. I'm going to use my light sort of like a ghost or a shadow to kind of see what all my quantum system is doing at the end of the day. And that's deeply rooted in quantum mechanics, like we have briefly discussed in our previous class. Okay, so we have sort of all the tools and nomenclature kind of there. What is shown here is the relevant nomenclature that we are going to use all the time. So with that in mind, now let's do something more useful. As I said earlier, we are never going to work with just wave functions because we don't care about wave functions. We don't. What we care about are coherences and population. And as we discussed the property of density matrix, the diagonal of the density matrix tells you the probability of occupation of a quantum state, population. The off-diagonal elements is telling you the projection, the coherence between states. And that's all matters. And all that element of density matrix will give everything that you desire for in an optical response, which will also give you window into everything about your material. Okay, so at the heart of it is a density matrix. So let's try to develop this density matrix formalism a bit more in detail. So in the context of that, an important kind of starting point is to be able to write out what are referred to as optical bloch Have you come across optical bloch equations anywhere? Quantum optics, yeah, lasers, kind of, it's the same thing at the end. So we're going to go over that a bit more. So let's write down the basics now. As I said, again, let's revive a bit for the sake of completeness. Your time evolution, density matrix, not transformed into interaction picture anymore. So my for spectroscopy, let's say we ignore the bath for now. There is no bath. System is isolated. Okay. For two level system, what will be the Hamiltonian for a two-level system? What kind of matrix will be the Hamiltonian?
2 by 2.
It's a 2 by 2 matrix. Very good. Let's start that out. Let's say for the sake of simplicity, I keep it still general. Keep it some B of t. Now what will be the elements of this 2 by 2 matrix? What will be the diagonal of this 2 by 2 matrix? Eigenenergies. Right? So there are two states, I call them 0 and 1, ground and first excited state. Off diagonal elements will be 0? It would be 0 if I'm taking a fully nice diagonalized Hilbert space. But now I have a problem, right? I'm dealing with a problem. I'm coming with light. Light is doing something, right? V of t is there, and V of t has to go in the off diagonal elements, right? Again, keeping it general. Okay, that's your Hamiltonian. Let's say your density matrix. What kind of density? What will be the dimension of my density matrix? By 2. Nothing spectacular. Let's name them this way. Okay, now if I want to write out explicitly equations of evolution, time evolution, or equation of motion for all the 4 elements of my density matrix, okay, I should be able to substitute these matrices back in my equation of motion. Okay, so essentially I need to be able to first write out expression for my commutator. Now this is reasonably straightforward. It's just matrix multiplication. If you're lazy, you can tell your computer to do it. If you're a bit more adventurous, you can kind of do it. It's not complicated. You don't need to be adventurous. You can just do it. I'm going to write it out, but I will strongly suggest at least once you should be able to do matrix multiplication and put them all together. So I'm going to do that. So my h rho minus rho h, very large matrix of elements. Be very careful the subscripts here. I always mess it up. Hopefully I didn't mess it up now. Okay, so now you have commutator bracket figured out. So you should be able to write down explicitly all the 4 equations of motion. Let's write them down. First term minus I over h cross 1 rho 0 speak 1 0 rho 0 1 rho 1 minus I over h cross E0 E1 1 plus 1 1 1 0 0 0 0 cross 1 0 1 0. Seem pretty boring, but it's kind of important to do it at least once. Zero, 0, 0, 1, 1. Okay, looks nice. There are a bunch of coupled rate equations, right? Just with 4 variables, right? They're coupled. As soon as you see something like that, you would be kind of tempted to write it in a different way. You would want to capture these set of equations in a form of a matrix, probably. But the density matrix is a 2 by 2 matrix. That's not going to allow you to do this. So I'm going to vectorize my density matrix. Okay, I'm going to convert my density matrix here, 4 elements with 2 by 2, into a column vector. Okay, if I do that, then I can get something very elegant. I'm going to slightly reorganize it instead of one, 0. Please verify this because it's derived from the above equations. Hopefully I got it right. It's always good to go back. Find this. As I said, this is basically some sort of vectorization of my density matrix. This is also that's a time derivative density matrix. This of the density matrix, and then I'm multiplying this with 4 by 4 vector, which I call L. It's an operator. So equation of motion, I can write it as vectorized density matrices. So this kind of vector form of the density matrix is called its Liouville representation. And this L in fact happens to be a Liouville operator. This Liouville operator has deep significance, especially when you're treating with system path interactions. It kind of naturally fits with some kind of when combined with some kind of Green's function, it can capture fluctuation and dissipation very effectively. We will talk briefly about that, but this is a general framework. In fact, these set of equations are in fact referred to as optical bloch equations. Okay, remember for light matter interaction, basically my interaction potentials V01 will be equal to V10 because coupling from the ground to excited state is same as excited ground state through a photon. Famous relationship combined stating that both of them are equivalent. About that, will be mu E. If you think about this, we are kind of formulating the problem so that we can just dump it all into a computer. It's kind of becoming into a form which is easy to compute, do all kind of numerics with it. So it's kind of going towards that direction. Okay, let's say for the moment, you don't have a field. The field is 0. Okay, Path field is 0. Of course, everything is stationary. Population is stationary. But then you have your diagonal of diagonal terms using the optical block equations. You can see are going to oscillate at the frequency provided they are not starting from 0. Let's say there is some, for some reason, there is some coherence existing in the system, and this coherence is going to oscillate at the frequency of energy difference between the two states. Not a surprising result. This is basically the definition of coherent superposition, right? Of course, if you don't have this coherence to begin with, this times 0 will be 0, so everything will be 0, and it's a boring result. But let's say for magically we are able to put some finite values here, then you will see this is going to oscillate at the energy splitting. Okay, so if you want to do this, now we want to come with our electromagnetic field. Let's say my electromagnetic field, my E of t, is oscillating at a frequency of omega. It's oscillating at the frequency of omega. So what I will do is I'm going to sit on top of this pulse of light, not pulse, the field. Okay, I'm going to transform myself into that frame which is rotating. So we transform into the rotating frame. Transform into the rotating. Not rotating from rotating wave approximation yet. We just transform into rotating frame. If I want to transform rotating frame, what I need to do is my transformed density matrix is going to be e power minus I omega t 1 t 0 e power plus I transformed 0 zeros will be the same as not transformed. 1. Okay. So in the rotating frame now, I can rewrite my optical block equations. Again, for the sake of convenience, it's going to look elegant now. Let's rewrite my optical block equation. So using rotating frame, now time evolution of my density matrix in the rotating frame. You might ask, why am I doing this? Not because I like writing big matrices, but it's going to look nice. I'll define omega in a moment. Delta is simply the detuning parameter. Omega sigma by omega r, which is your Rabi frequency. Okay. Right. This is optical block equations of your density matrix in the rotating frame. Okay. I mean, already kind of we have seen in the previous form, but here it looks even more elegant. You can kind of see that this large 4x4 matrix has some kind of modular form, right? There are a bunch of zeros here. Eigenenergies kind of are here. All the interactions are here. They're kind of in a very nice modular form. It's kind of elegant to look at. But let's focus on this light matter interaction term here, which has, of course, the Rabi frequency there, but you have these two parts to it. Okay. Remember, in the rotating frame, all the frequencies are shifted by omega. That's why you have to add this omega here. You're shifting everything because you're moving on to the frame of reference of your electromagnetic wave, which is oscillating at omega. So all the frequency energies will have that additional offset in the rotating frame. But in the rotating frame, there is a term which is constant and term which is oscillating at twice the frequency. When you actually try to integrate this equation of motion, if I try to integrate, for example, something which is oscillating at very fast, twice the frequency, multiplied by a function which is slowly varying in time, would kind of say that this is negligible. So now I can make formally my rotating wave approximation. My rotating wave approximation, or A, is basically saying of T is simply a constant. Okay, so that kind of gives you a overview of optical block equations, which are going to be very, very helpful. We're going to kind of use it on and off, but it's kind of a basis of what we are going to do right now. Right? We have kind of introduced time evolution part. But what is missing right now in this set of equations? Bath. Bath is completely missing. Now, one way of introducing the bath is through a phenomenological term. Meaning what? Meaning that you know that when I have a bath interaction, you're going to add some kind of damping term, and this damping term in time is going to give me some kind of exponential decay. I know it. So I could kind of introduce a damping term with some phenomenological parameter gamma. I could do that. In fact, in the next tomorrow's class, we are going to do that kind of to show something. But for today's class, let's say we want to be a bit more rigorous. We don't like phenomenological. I hope everybody understands what phenomenological is. Phenomenological is driven by phenomena, so you kind of expect a process to happen that way. So you, even though there is no real physical basis, you kind of introduce terms which kind of make sense in the context of specific processes, specific phenomena. So for today, let's say we want to be a bit more rigorous, and let's try to do this in a, I wouldn't say extremely rigorous way, but at least a bit more rigorous than what is done right now. Okay? Clear so far? Clear so far? Good. So the idea is now we have to introduce sources of dissipation or relaxation or bath coupling, whatever you want to call it, explicitly. Okay. Let's again take a two-level system. Let's be a bit more rigorous in defining this. The reason I'm also doing this is because I want to start playing around with Q-tip. So I'm going to use starting to use the language of Q-tip already, so that you kind of. So let's start again. I said we start with dissipation, but I'm going to start with saying let's forget dissipation for now because we want to try to reformulate it. Hold that thought for now. So let's rewrite our d rho by dt cross rho. We know all of this. Now I'm going to say my system this stuff. I'm going to define it of the matrix like before. Are you comfortable with such formulation? Do you know what this is?
Polymmetry.
Okay, so you can kind of show this that if I have sigma z, this one, then this is basically equivalent, right? Want you to go back and convince yourself. I am not going to convince you. You convince yourself about this. Okay, fine. Now we need to add interaction, light, that we all know, seen. We keep seeing it all the time. So V of t, I'm going to call for now hi t. Define this, of course, assuming that my E of t is E naught cos omega t. It's going to be minus h cross. So the interaction always has to have off diagonal elements, right? So I need to have form which looks like this. There is a specific name for these kind of operators. These are called collapse operators. Have you come across this anytime? In fact, Qtube uses collapse operators, which are basically these as defined. So this, for example, is a raising operator. This is a lowering operator. These are collapsing on one state or the other. So you could write this more explicitly. Great thing about this, for the way I'm putting this, is that you can open your Qtip and you can define these specific operators. It has a library of operators which are defined in this particular language formalism, so you'll be able to use it very easily. But at the end of it, it's not magical. It kind of has the same physical basis you are kind of comfortable already. Okay, so let's expand this out. Your interaction Hamiltonian yeah, there are 4 terms there. And of course, you will say, I'm going to ignore 2 terms. Right? Why are we going to ignore 2 terms? Rotating wave approximation. Which of those 2 terms shall we ignore? It's very hard for now because we have not seen the formalism yet. I'm going to tell you, I'm going to show you as well. So sigma plus e power this and sigma minus I omega t. These two will be slowly varying and cannot be ignored. On the other hand, these two are going to oscillate at fast frequencies, rapidly oscillating terms, and can be ignored. Now you might ask me why. Don't you want to ask me why? No, you can ask me why. It again, you can show it from first principles again. I should not call it first from fundamentals. So let's kind of briefly take a detour and kind of show it for the sake of getting more comfortable with using operators and so on and so forth. So let's say, is there a way to show, for example, these two terms are going to be oscillating at fast frequency, for example. So if to do that, remember we are working in interaction picture. Slight detour here. If you don't want to kind of worry about advanced quantum mechanics, switch off for now. Those who are kind of want to kind of get a sense of more advanced quantum mechanics, let's go through this. So in interaction picture, you all know when I transform any operator from Schrodinger to interaction picture, how am I going to do it? So any operator in the interaction picture is e power I h naught t h cross. My operator in Schrodinger picture e power minus I h naught t over h cross. Right? What are these? What are these operators? Time evolution operators, kind of related to time evolution operators, but this is unitary transformation. Good. Now, if I want to do this for, let's say, sigma plus my raising operator, you will see this is e power I h naught t h cross sigma plus e power minus I h naught t h cross. But now I know what is h naught, right? I kind of defined it. So if I get that definition in and kind of write it out, say my sigma plus in the interaction picture will be e power I omega naught t sigma plus. Similarly, sigma minus in the interaction picture will be e power minus I omega naught t sigma minus. If you kind of put this back into your interaction Hamiltonian, write it out, you will see, in fact, that the terms that I identified earlier as a slowly varying, in fact, close to resonance, there will be a term which will be varying slowly. Let me explicitly write that down. So if I just take these two terms which are slowly varying, then my interaction Hamiltonian in the interaction picture will be minus h cross sigma minus e power I. Remember, this sigma is lowering operator in the interaction picture, minus omega naught t plus sigma plus minus I omega minus omega naught t. And it's not complicated to see that under a condition where omega is almost equal to omega naught, these two terms will be slowly varying, the other two terms will be very fastly varying. So I can just keep these terms which are slowly varying, ignore the other terms. Basically, this is rotating wave approximation. Okay. Sorry. Did I move it too fast? It's fine. Everybody's fine. Okay. The takeaway message is that my interaction potential V of t my interaction potential V or rotating wave approximation will be minus h cross sigma minus e power I omega t plus sigma plus e power minus I. Okay. So again, if I want to explicitly write things out as a summary, you have not followed so far, you just need to follow this. My total Hamiltonian now, and this formalism is not that different from other formalisms. Using specific operators. Omega octal is your cross plus is your raising operator minus is your lowering operator. Everybody comfortable with this? It's very powerful because you will see that expression that I wrote, you can directly take that literally and put in the Q-tip. It's a one-line code. It kind of makes our life very easy to kind of simulate very different kinds of Hamiltonians. If I write it out in this kind of form using polymatrices or raising lowering operators, which all can be defined easily in Q-tip. Okay, one last thing I want to complicate a bit more. No, I'm not complicating. I'm actually simplify life, which we have done already earlier, just before when we were deriving optical block equations. You always want to be in the rotating frame. You have done the rotating wave approximation, which means the removed terms which are fast oscillate, but we are still in a frame where my field is going very fast. So let's write the field. Okay, so if I transform, I need to transform this into a rotating frame. So the driving frequency is omega. I need to be able to go into that rotating frame. Okay, so I need to go from this, put tilde on top just to represent the rotating frame. And quantum mechanically, when you want to do this transformation, it's equivalent to moving to interaction picture. Actually, it's exactly that. Okay, so it's as simple as that. So you have some unitary operation, exactly like before, acting on the density matrix. U naught of t c power I omega t sigma z over 2. You all know this. That's the advantage of power of time evolution operators. Then do a different thing. Now to do this transformation, so this is transformation. Your rotating frame, you're moving the density matrix in. Okay, but what we need to write is that of the Hamiltonian. I need to be able to write the Hamiltonian rotating frame. Density matrix is the thing that I'm interested in. That's why I want to kind of evaluate my density matrix in the rotating frame. Simply by transforming this doesn't mean that I have transformed my Hamiltonian. Okay, so you need to transform the Hamiltonian. Again, you can do the same thing. You can do the same kind of trick. The only thing that you need to remember when you transform the Hamiltonian, that there will be an energy correction when you do the unitary transformation. That's an additional thing. Okay, so that's not something I'm going to explain or elucidate in this particular course, because that becomes a completely different topic. So I'm going to just say, then if I have to go from my H, let's say call it H prime, I can do the same thing. but I also need to have another correction term, something like this. If I have a rotating thing, so if I even in classical mechanics, right, if I make a transformation from static frame to a rotating frame, you will generate additional energies coming from Coriolis forces, right? There is some kind of energy correction happening as soon as you go, because there's additional kind of forces, centrifugal forces that come into the picture, even in the classical sense. The same way you have similar kind of correction here, which is a bit involved, but it's not complicated. Basically, this is transformation into interaction picture. And this is kind of an inertial term. If you remember your classical mechanics, it's basically kind of effective energy shift. Okay, cool. If I do this now, I can rewrite my transform Hamiltonian in the rotating frame, interaction picture, rotating wave approximation to be this. Where delta here is detuning. Basically, the energy difference between my system and my driving frequency, driving field. Okay. Kind of looks extremely elegant if you think about it. Okay, fine, comfortable with this? Questions? Okay, let's probably take a small break here. The reason I'm saying small break is because now we have reached so far in a very complicated way, but at the end of the day, we haven't introduced the actual thing that we wanted to introduce, which is dissipation. There is no, I have basically complicated my life unnecessarily because I already solved what I want to know, but now I'm in a picture which is more complicated, seemingly complicated, but without dissipation. So the next step is to introduce dissipation. Okay, so the way to do it, I'll just write the equation that we need to work with. These are what is called Lindblad dynamics. We'll speak about it a bit more. This is the basis of spectroscopy, really. So your d rho over dt. Of course, you have your minus I over h cross. H rho, in this case, of course, it will be h prime. And then you have to add a dissipation term, dissipative term, or relaxation term. This is coming through path interaction. Okay, so we'll talk about, again, this is deeply rooted in quantum dynamics. This is not a class of quantum dynamics, but I'm going to, after the break, invoke certain formalisms, some forms, not necessarily derive them, but kind of invoke them, specifically in the context of two things, two processes that happen in real life spectroscopy. You photoexcite the system will decay. When it decays, it emits light. You all measure it. You measure photoluminescence, spontaneous emission. That's a reality. Okay, that's one thing. The other thing is, I generate, assume it's a coherent excitation. I'm generating an ensemble of molecules which are all oscillating in phase. Over a period of time, they will dephase. These are the two dissipative processes: spontaneous emission and dephasing process. So we are going to see functional form of these two. I'm not going to derive them. I'm not going to show them. I'm going to invoke them. Okay, and then after that, we'll have our tools to kind of simulate stuff. Then we'll go into Qt. Okay, let's take a short break.